starting with set notation, I'm just going to solve these two inequalities and say what values of x satisfy both. So we just treat them as an equal sign, except if we have to multiply or divide by a negative number, which isn't an option, isn't an issue here. One inequality gives us an upper limit, one gives us a lower limit, so our overall answer is a combination of both. Okay, so the answer to that first one looks like that. So if the question said giving your answer in set notation, and this is only an issue if it does say that explicitly, all we would do is we would change it. We would say x is a member of the set of those numbers there, so that's x colon that, and we would put that in the curly brackets. So that is that answer given in set notation. Simple as that, nothing more complicated than that. And we only need to do that if it explicitly asks for set notation. Second one is a little bit more fiddly, so I add an x and so x is greater than 3, and here it comes out with x is less than 2. So there's no overlap there. There's no overlap. So what we say is that x can be that, or x can be that. So I'm going to put those two in curly brackets. Sorry, my curly brackets are nearly as bad as my thetas. And it's this or this, so using Venn diagram notation, not intersection, there's no intersection, that would be an intersection, but we have to say that union that. So that's using the union sign that we used with Venn diagrams, same thing. And that is set notation. That's it. Nothing more complicated, nothing less complicated.
So, just for if you forgot the set notation.
Good question.
What mark would that be?
I don't know. Yeah, I cannot give you an answer to that question. Yeah, if it says in set notation and you just give it with the blue, I don't know. I imagine you use one mark.
Yeah.
It would seem harsh, but there we go. So let's just do a quadratic inequality, just for sort of completeness. I'm a bit of a completist. So remember, with quadratic inequalities, just like with quadratic equations, line it up, equal to 0. Think about where the roots are, where does it equal 0. Do a quick sketch as if it was a y equals that quadratic, and then decide, are we talking about where it's below the axis or above the axis? That's for part A, and then you've got a combination question in part B, which hopefully you can answer using set notation. Yes.
2 times by minus 1, flip the sign.
Yes. I'm going to do it slightly differently. We'll end up the same answer. I'm going to put everything on the right hand side, so I don't need to do that. But yeah, if you do that, you'll have to flip the sign. We'll end up with the same answer. I manufacturise because I don't want to lose those skills. So I solved it as if it was a normal quadratic equation, equals to 0. But then I said, right, actually, if that's a graph, those are the roots, and I know it's a happy quadratic, so it would look like that. What we're actually asking, when is this less than 0? You would have got the same, which is below. So it's a sandwich rather than a tails. So my answer to A is no extra lines, because there's no extra line here. Now I'm asked to combine that with the other inequality, x is greater than 1. So there is an overlap here. All it means is I've just got to change that to 1 because minus 2 to 6 satisfies that one, but between minus 2 and 1 it doesn't satisfy that one. So I change that, and then I'm just going to make that into set notation by adding the x colon and the curly brackets. And that's how you would answer that question in set notation. Great, we're not going to do any more. Tick that off. If you've got your formula books, this would be a good time to whip them out. If not, Page 6 actually has the formula for differentiation by first principles in. We've done this before. This is this idea that the idea that when you are differentiating, you multiply by the power, reduce the power by 1. That's not just random. Someone proved it and only realised that you could do it by multiplying by 1 and multiply by the power and reducing the power by 1 when they'd gone through this process for lots of functions. The predictability was realised. So if you remember, when you've got some function and you want to work out a formula for the gradient, the way first principles works, and it's genius really, is you say, right, let's pick, so this is my function, this is what y equals, isn't it? So if you take a point and say, right, that's when x is that, the y value will be whatever you get from that function when you make x equal to that number there. And then you say, right, well, the gradient at that point, I can estimate it by drawing in a chord. And that point is a little bit further along in the x direction. So we say, let's make it x plus h. And so the y value will be what you get from this when you make x equal to x plus h. So we call that. And then to work out the gradient, we do the bishop. You know, all those years we've been doing the bishop, we do this divided by this. To work out this distance here, it's that number, take away that number. So that's and this distance here is just h, because I've gone from x to x plus h, so it's just h. And we know that as we make h much, much, much smaller, so as we make h equal to smaller, that gradient is pretty much the same as the gradient of the line there, so it gives us this formula for the gradient of the curve. dy by dx, f dash of x, same thing. So that formula's there. I'm not sure how useful it is, but there we go, it's there. Let's do an example. So let's do an example we've done before, and then we'll do trig. So let's take x cubed. So when x is x, y will be that value cubed. And when x is x plus h, I've got to take whatever the value of x is and cube it. So this is what you get when you expand those brackets. And you can either do that with the binomial, or you can multiply out two lots of x plus h and multiply the answer by the final x plus h. You then take away that, take away x cubed, divide it all by h, and then we're into just some algebra. And then we consider, once we've done as much algebra as we can, what happens when h gets really, really small? So go on, have a go. See if you can start by multiplying that out to see what we get. Now we know the answer, don't we? We know that when you differentiate x cubed, you get 3x squared. So we know what we're aiming for. So that's quite nice in a way. You know, we can sort of maybe use that to guide what we're doing in some way. So we should get, when we multiply out the bracket, this. That's my f of x plus h. And in this case it's x cubed, so it's x plus h cubed. Remember, we're working out this distance here, so we do that, take away that. So all of that, take away x cubed, just means that the x cubes cancel out. So you're left with 3x squared h plus 3xh squared plus h cubed, all divided by h. Don't ask at this point what you get when x is 0, because that's going to give you problems with your denominator. There's good news though, isn't there? I can divide everything by h. I can only simplify this if everything's got an h in it, but it has. So that h simplifies with that one of those, and one of those. So I get 3x squared plus 3xh plus h squared. Now, the limit of that as h tends to 0, well, there's no h there at all, so that isn't affected. When this becomes nothing, that whole term will become nothing. And when that becomes nothing, that whole term will become nothing. So we're left with 3x squared, which is what we knew we were going to get all along. Good news. Good news. Differentiation by first principles, explicitly mentioned, forget which paper. So there's going to be a question on it, and they tend to be pretty straightforward. Prove, using differentiation by first principles, that f dash of x for f of x is x cubed is 3x squared. However, sine and cos are on the syllabus as proofs that we need to understand. So let's look at how we can prove by first principles what we already know about differentiating sine and cos. We know that when you differentiate sine you get cos, and when you differentiate cos you get minus sine. So let's start with sine. So doesn't matter which, you don't even have to draw a diagram really, it doesn't matter which bit of the curve. And you don't have to worry about the negative thing, because when you do this, take away this, you'll get that negative value anyway. So let's say this is my original point. X and y will be equal to the sine of that angle. This is a little bit bigger than x, so it'll be the sine of an angle that's a little bit bigger than x. So using the same formula from before, which is on the formula sheet, the formula for the gradient is that, take away that. Divided by that, take away that, which is just h, and that's always just h on the bottom. Now remember, I know what the answer is. The answer is cos. I see no causes. But I do see something that rings a bell. Particularly as I've already got page 6 on my formula book open in front of me. Because one of the first things we did this year with Trig was we talked about we had these angle addition formulas which we use to make all sorts of identities. We sometimes use them as they are. So the sine of A plus B is not just the sine of those two angles added together, it's more complicated than that. So if I make A equal to x and B equal to h, I can write that out using this formula. Remember, the plus minus there is that if it's sine of A plus B, which it is in this case, x plus h, we have a plus between the two. If it's minus, we have minus. It's the other way around for cos. We'll do cos in a minute. So go on, see if you can expand this. Don't forget you've got the minus x at the end all along as well. So okay, expanding that, use the formula, but you still do minus x into that, take away that, minus sine x, sorry. Now, I've got a cos, but there's still, I'm still a long way from just cos x on its own. But remember what we're about to do. We're about to say, and we're dealing with angles here. Our x-axis will be angles, so yeah, the x values are angles, and h will be an angle as well, won't it? We've moved x on a little bit, so we've moved it on by a little angle. So h is a small angle. In fact, we're about to make it really, really small. And good job we've got page 6 open on our formula book, because there's something else on the formula book about small angles, isn't there? We know that for small angles we can, well, I say simplify. With cos it doesn't really simplify it, but we can estimate the value of sine, cos and tan even if we don't know the angle itself. If we know it's small, I know that the sine of the angle, so we've got a sine h, we've got a sine h in our expression, so we know that's roughly the same as h. So this I can replace with just h. Now if I put the h after it, I suppose I could write times h. I'm instead going to write it in front of it. So the sine h is roughly the same as h itself. Cos is never, well actually it's tan that's normally the complicated one, but cos in this case is not as straightforward. The cos of h will be 1 minus h squared over 2. I don't need to prove those. And don't forget, all along we've got that minus sine x as well. So I've got sine x times this plus h times cos x. Take away sine over h. I'm going to multiply this bracket out. I've got sine x times 1 and sine x times minus h squared over 2. So I'm going to write the minus h squared over 2 in front of it, because that's not part of the angle, plus h cos x minus sine x, that's been there all along, all divided by h. Now some of you can already see what's going on here. The sine x's are going to disappear, aren't they? You've got sine x, take away sine x. I can then divide both of these terms by h. I've got an h in everything, so that will cancel out that and one of those. So what I'm left with, I'll have to write it up here because I've run out of space, is minus h over 2 sine x plus cos x. And I'm asking what happens when h becomes really, really small. That's going to become nothing. Because 0 times sine x will just be 0. So we get cos x, which is what we were expecting to get all along. When you differentiate sine x, you get cos x. Saying that they had from now, I'm not sure that's something I would even begin to try memorising, but I'm sort of hoping you'd be able to reproduce it at a push. Let's test that by trying it for cos. So cos is pretty much, it's the same shape, isn't it? You could take it anywhere on the curve. You don't need to do the drawing. I think I always would, but so you've got your sine x proof. So now see if you can do it for cos x. We know what the answer is going to be. The answer is going to be minus sine x. When I differentiate cos, I get minus sine. So, go back up to the formwork. There's the cos A plus B rule. Just be careful, if it's cos A plus B, you've got a minus sign between the two terms. It's not the same, but it's almost the same. See, look, I forgot the minus cos x. Really easy to do. And that's quite a nice drill because it goes through, it uses small angle approximations, uses the sine A plus B formula, revises first principles. So it's it's quite a nice cover-all thing to do. You don't need a paragraph explaining why that term disappears. It's just enough to say the limit as x tends to 0. Okay, so that's differential by first principles ticked off, and that I think that really is the end of the content. Absolutely the end of it. I'm sure we may come across other things. And this is where I rely very often on people doing practice papers and coming with questions, because sometimes it prompts me to either revise something that I perhaps didn't teach very thoroughly, or maybe every now and then it throws up something that we skipped. I don't think there are such things, but you never know. You never know. So let's just spend, I want in weeks to try and sort of fill in any 5-10 minutes we have spare with little things we've already revised. So particularly if you were here on the Wednesday after school things, I'm hoping you will know the difference between, the difference and what they have in common between these two expressions. Firstly, could anyone explain what they have in common? You can write them both to the power, and because of that we can expand them both using binomial techniques. And it's good job we've got our formula book open. If you turn back a page in your formula book, you will see you've got both binomial techniques written out. I find the first binomial technique that we did last year, the a plus b to the n one in the formula book, completely unnecessarily confusing, so I'd much rather just remember how to do that one. Remember, that works when a and b can be anything, n's got to be a positive whole number. And then this year we met the 1 plus x to the n, and that's a series expansion that goes on forever, so we're always told how many terms to do. The first thing in the bracket has to be 1. This thing has to be between -1 and +1, so if we're replacing it with minus 2x, then x would have to be between -1/2 and 1/2. N can be anything though, and in this case it's going to be 1/2, isn't it? This one here, we can just do it because of the predictability of the expansion. You're going to get a to the power of 4 in the first term, and then a cubed times b in the second term, and then a squared, b squared in the third term. Each term will have a coefficient. 5 terms, so we're looking for Pascal's triangle with 5 coefficients, or calculator. I think we did this just the other. Well, sorry, no, we did it on the Wednesday after school, didn't we? So let me just remind you how to get NCR on your calculator. it's option, second page, probability, and there it is. So option, second page, probability, there it is, NCR. Remember, the coefficients are symmetrical. The first one is always 1, the second one is always the same as the power. So you actually only need to work out one coefficient in that first expansion. So just see if you can have a go at those two. So with NCR, the N is the power from the question, and the R is the power of B. So I only actually need to work out the third term, so that's going to be NC2. It's NC0, NC1, NC2, NC3, NC4.
So,
Yes.
in an exam, when they ask you to do this, would they ever ask you to work out like a degree by power, or would that be a bit?
Work out a.
Like if it was to the power of like 20 or something?
Yeah, they could do. You might find they wouldn't ask you to do the full expansion, but they might ask for the x squared term. So you'd have to work out, you know, in this, you'd have to work out where the x squared term would be. It would be that one there. So you'd have to, yeah, you could have a big power.
Okay.
I mean, I'm far more likely to get one of the right-hand ones. But yeah, you could get one like that. Did I say 4 terms in the second one? Just 4 terms. I remember 1 is the first term, so actually it's only 3 terms. Just be careful that you, when you're squaring, cubing, doing that to power of 4, you square the 2 and the x separately. I always think the formula book's not particularly helpful for the second one as well, but so I just remember the first term is 1, second term doesn't have a denominator, third term is 2 and fourth term is 6. Just got to do the tops. I think that's right.